So we're going to be looking at valves tonight and different terms we use when we buy valves and we size valves and we service valves. This is the mainstay of instrumentation valves, our main modulating valve. It's called the globe valve. It used to have a globular casting in the olden days, that's why they called it the globe valve. Important things to note about the globe valve are, well, let's get my pointer. There's my pointer. Right. Pointer. Got it. Okay. Most of it was casting. The bits that did the controlling, in this case a plug, a seat, and the stem, those bits are called the primary trim. And those are the bits that do the controlling. Anything that's left over, which normally consists of nothing much more than the seal, we call that the secondary trim. Whenever we're dealing with any process control thing, whether it's a valve or a flow tube or whatever, we always worry about what comes into contact with the actual process. And the parts of the valve that come into contact with the process, they're called the wetted parts. And we're often asked to specify the wetted parts, and so you have to be aware of what the process is so you can specify the wetted parts. So we have the primary trim, which is the bits that change the flow. Now, what's important to realize is that you can get a 100 ml valve, and the primary trim in it is designed to control, say, 10 litres a minute. Or you can get exactly the same valve, but with a totally different primary trim, and it controls maybe 1 litre a minute. So the size, the physical size of a valve doesn't necessarily show you how much it can control. This is a typical globe valve. Here is the valve part, just here. So that's the valve. This bit up here is the actuator. That's what moves the valve up and down. And this box here, that's the positioner. Over here we've got a cutaway drawing of the valve. This valve, instead of having a plug and seat, it's got what's called a plug and cage. So you've got this cage thing, and it's got big holes in it. Big holes in it, like these big holes. And the liquid goes through the holes and out. So the plug and seat valve, it's like a plug and cage, but I'm sorry, a plug and cage, like a plug and seat, but it's got a cage. So the same valve can have different primary trims. Often we just call it the trim. And the different trim can give the valve different characteristics. For instance, you can have what's called a quick opening valve. With a quick opening valve, this is open, this is flow. With a quick opening valve, when you open it a little bit, loads of flow comes out. That's quick opening. This valve here, that's equal percentage valve. With an equal percentage valve, that's flow up there, that's open, equal percentage valve, it opens like that. It's called equal percentage because for every percentage increase, the flow increases by an equal amount. Seems strange anyway. This valve here, this is a linear valve. Now, what this is supposed to do is it's supposed to give you, there's open and flow, this is supposed to give you a linear response. I'm a bit dubious about whether that works or not, but anyway. And this valve here, this one is a quiet valve. There are occasions when you need a valve not to be making the constant sort of shushing and bubbling noise that valves make. So that's a whisper trim valve. Now, there are single-seated valves. This is a single-seated valve. It's got one seat and one plug. Problem with a single-seated valve is, if with the flow going in the direction that this flow is going here, the flow, the pump basically, is pushing that plug up. So in order to push that plug back down, we need to have a great big, fat, strong actuator on there. So a single-seated valve has got to have a strong actuator to shut the valve. Or if the flow happened to be going the other way, it needs to have a strong actuator to open the valve. This is a double-seated valve. Now with a double-seated valve, the flow is pushing that plug closed, but it's pushing that plug open. So the forces are more balanced. They're not perfectly balanced because of the fact that the bottom plug here has got to be able to fit through the top seat so that the whole thing can be withdrawn for servicing. So they're virtually balanced. Now, for that reason, that's right, that's a double. Because it's much more balanced, you don't need such a big actuator. But the problem you get is that you have metal-to-metal seals. And when you have a metal-to-metal seal here and a metal-to-metal seal here, the way you seal a valve is you can actually unscrew this stem. The stem rotates because it's threaded at the top here. So what you do is you rotate the stem. Well, sorry, firstly you close the actuator fully, so you push the actuator all the way down fully. And then you rotate the stem until it just pushes back a little bit. And then when it just pushes back a little bit, you know that it's seated. Now what you're supposed to do is you're supposed to get in and you're supposed to adjust only one of the seats will be seated at this point, because you can't have it seated on both the seats. So you're supposed to get in and adjust the other seat until it's tight on both seats, but you can never get it tight on two seats. Fact is, you cannot simultaneously seal two metal-to-metal seals. So a double-seated valve tends to leak a little bit. We say it passes. Here's a double-seated valve, and here's the first seat. Oh, I could do with a better colour than that, couldn't I? Here's the first seat, and here's the second seat. Fact is, if you wanted to have a single-seated valve this size, the actuator would have to be absolutely humongous. While we're looking at this valve, I'd just like to point out some other things. At the top here we have a spring. This is a spring return valve, and it's a strong spring. This is a very, very strong spring. Valve actuators generally have very strong springs on them, so you're always a little bit careful when dealing with a valve actuator, because if you just unscrew it willy-nilly and that spring comes out, it comes out with some degree of force. Just here, of course, that's the diaphragm, and we blow air into the top and it pushes the stem downwards in this case. So, rules we have are general sort of rules. Single-seated valves, you need a bigger actuator to oppose what we call the hydrodynamic forces. Basically that means, oh, do a little bit of pen there. Basically, hydrodynamic forces means the pump. So you need to have a bigger actuator. But it seals really, really tight. Whereas a double-seated one, you get a smaller actuator, but it's almost certainly going to leak. Actually, a general rule is bigger, two G's, actuator leads to tighter seal, because the bigger the actuator, the more it can push down. Okay. This is a three-way valve. Three-way valve, or a three-port valve. This is a three-way valve. It's a diverting valve. And the idea is the flow comes in over here, and it's diverted either up this way or down this way. Easy concept. Now, problems we get with three-way valves is, well, problems we get with all valves is that quite often people put them in the wrong way round. Now, if we look at this valve, if it was piped up the wrong way round, with the flow coming in from this direction, what would that make the valve into? What type of valve would it become instead of a three-way? Yeah, pretty well. It becomes a shut-off valve. All it does is open and close the flow. That's a real problem. One of the important things to notice about a three-way valve is that the flow going in is always maintained. So there's always the same flow going in because it's either going at the top or it's going at the bottom. So you always have the same flow in, but if you pipe this up the wrong way, you're able to shut the flow off, and that can be a real danger. Let's get rid of some of these. Right. This is a mixing valve, and this is a mixing valve very similar to the valve you might have on your kitchen sink, where you might have hot water and cold water coming in, and what goes out there is warm water. So it's just a simple mixing valve. What happens, looking at this then, what would happen to a mixing valve like this if it was piped up the wrong way so that the flow came in that way? What does this mixing valve turn into? Yep, if you pipe it the wrong way, the mixing valve turns into a diverting valve. Now let me just go backwards and forwards here. Diverting valve, mixing valve, diverting valve, mixing valve. They look incredibly similar. In fact, the castings are the same. So externally, they will look identical. They'll be painted the same color. They'll look absolutely identical. They're quite often used in pairs. Here's a situation where we're using it in pairs. What we're doing is we're controlling the pressure in the top of a paper machine head box. This is a head box. There's a head box. So we're controlling what's called the air pad pressure in the top of a paper machine head box. And by opening and closing these valves, and what I'm trying to show here is that when one of the valves, I could do it with a different color. When one of the valves opens, the opposite valve closes. They work in pairs. So this is quite a common application for a mixing diverting valve pair. Now what's going to happen is that the fitters will come along and they'll take these valves away to be serviced. Then they bring the valves back and they fit them up, and we come along and we connect up our little 4 to 20 milliamp signal. Now the problem is that if the fitters fit the wrong valve in the wrong place, or fit either of these valves facing the wrong way, it's our fault. We take the blame as the instrument people. So you've got to make sure that the correct valve is in the correct place, facing the correct direction. Here's another use for a mixing valve, and I've also introduced another type of valve which is called a balancing valve. Now, if we didn't have a balancing valve, it would cause us some problems. To demonstrate this, I'll do the electrical circuit equivalent of this thing. Okay, that's the electrical circuit equivalent of this plumbing circuit. Now, what would happen if the switch went here? Yep, we've got a dead short. And a dead short causes massive flow. So you get this massive flow, and that causes masses of heat and overheat, and the battery blows up. So that would be a bad thing. So to fix this, what we do is we put a resistor just there. That restricts the flow. Now, the same thing would happen on this boiler system. If the bypass valve were to go into full, if the bypass valve would go into full bypass, so that the flow was coming in that direction, if we didn't have a valve in there, a balancing valve, oops, I shouldn't have done that. If we didn't have a balancing valve, then the thing would short circuit. Hot water would rush out of the boiler and short circuit straight back to the boiler. The boiler would then say, oh my goodness me, I'm awfully hot, I'm just about to blow up. And the boiler goes into emergency shutdown. Now, when a boiler goes into shutdown, it goes through its purge cycle and its clean cycle and all its nice shutdown cycle. And shutting down a boiler can take probably about 15 minutes. Now, during that 15 minutes, of course, the heat exchanger cooled down. So now there's a need to turn the boiler back on. There's a boiler call. So the boiler starts back up. But starting a boiler can take another 15 minutes. So now what's just happened is the boiler shut down for 15 minutes, and it takes 15 minutes to restart. So then it starts up and it runs for a little while, and then of course it goes on to bypass and it shuts down. So what the boiler is doing is it's doing this. It's going on, off, on, off, on, off. We call that short cycling. Short cycling is horrendously expensive. It uses a lot of energy because you're constantly purging the unburnt fuel out of the boiler. The boiler is not burning efficiently. It's not got up to its temperature. So it's a very inefficient thing to do. In addition to that, boilers are designed to run hot. They're designed to be continuously hot. And if you don't run a boiler hot, then it tends to leak, and water leaks out of it everywhere. And that's not a good thing. The other very bad thing is that most boilers are made out of cast iron, and if you keep heating and cooling and heating and cooling them, you will crack the boiler. And, well, that's quite unpleasant as well, and it's not popular.